So far, we have established the probability of have a high discrepancy, the risk of have high discrepancy of evaluating a hypothesis in a certain sized training data set and its generalization error. And we have also discussed some basic probability theory, considering the sample space, what is the event of question, and its link to the probability. And we have also discussed that in our problem of discussing the generalization risk, the sample space is defined by the fact that the training set for whatever size. Note that we have used the sample capital omega for the sample space, but now we have changed the symbol to represent that is for data set. So the sample space is defined by the fact that we have randomly drawn some number of samples from the data space. So this figure illustrates that we have drawn 4 samples from the data space, which makes the sample space of training data set, and of course that is also the source of randomization of stochasticity of the training process. So learning from data is a random business because of this randomness. We need to distinguish between these two spaces. For the data space, we consider for the predictive nature of the task, we consider the link between some data attribute, the data, and the target value. We consider a hypothesis of the value, and where the hypothesis makes errors, which defines the generalization error or the out of sample error, while how it links with the sample space of training data sets. Say if the out of sample error is something like 0.24, and for this hypothesis, we then define some tolerance. Say we would like the in sample error and out sample error to differ less than 0.1. Then for any data set in the sample space of d to the power 4 that contains 4 training samples, if it happens that the evaluation of this hypothesis is error, correct, so have 1 error, then the evaluated in sample error will be 0.25, which satisfy our tolerance, and we consider that is a good data set for the purpose of evaluating this hypothesis. If on the other hand, say the H predicts all data samples correctly in the for all the 4 samples in the data set, then we will see that this data set in this sample space is a bad data sample, a bad training data set. Because if you choose to trust the in sample error evaluated on this particular set, you will be wrong when it comes to measuring the out of sample error of the hypothesis. And therefore, for the hypothesis, for the determined tolerance, we will have a bad area, a bad region, which is of course not a continuous region as we have mentioned, in the sample space of training data sets, those are bad data sets. If you evaluate the hypothesis here, the evaluation will be wrong, will be very wrong according to the tolerance. And the Hofstad's inequality says when the n increases, the area of such region decreases exponentially, which is a good thing. And the challenge we encounter is we are not happy with Hofstad's inequality for the learning process because that deals with a single hypothesis. However, what we want is let me introduce a sample denotation. We call this is a bad event for H. So the event is of course defined by n training samples. This is bad because if you evaluate H on this training sample, the error will be exceeding the tolerance. On the other hand, what we are really concerned is what is a bad event for a learning process, the process of select some H star from some hypothesis family, and the selected H star, when evaluated on a data set, the evaluation will be within or exceeding the tolerance. Say we call if for now let us represent the size of we need to define the size later. The size of the hypothesis family to be m. Let us call the bad event for this learning process of selecting the selected H star to be Bm. We are concerned with this probability because we probably do not want to deal with all the complication of the learning process, and for the learning itself, we haven't determined which algorithm we want to use, which hypothesis family. We just refer that process as generically as some process, some learning procedure. So if we want to discuss the probability of a bad event happen, the bad event means the given data training data set happen to be a bad set for our learning procedure. This bad event happen for the learning procedure. We'd better to discuss that using simpler terms. So we may want to see, okay, the given data set happens to be bad for the selected H. This probability is up-bounded. It must be smaller than any of the hypotheses within the hypothesis family, any individual one. The given training data set is bad for this particular hypothesis. If we take the union of all those bad events, this must include the event that the given training set is bad for the selected one. And this itself is then upper bounded by the sum of the probability of those individual bad events. And that is because when we consider the union, the probability of the union of events, there might be overlappings of those events. Some data set can be within the bad area, bad event region for one hypothesis and also for other hypotheses. But if we take the sum of them, we calculate them separately. So this is a naive risk bound for learning within multiple hypotheses, learning within hypothesis family. This intuitive bound works only for maybe the most simplistic scenarios. It does not work generally. We immediately will encounter practical problems. For one thing, the badness of this event, the bad event itself is described by the fact that a hypothesis differs from the out-of-sample error when evaluated in the training set exceeding some threshold, some tolerance. However, the out-of-sample error Eout is not computable because we do not have access to the general data distribution. So basically, this event is not we are not able to test the event for any given data set. So this is not computable. And also, very importantly, for any practically useful hypothesis family, such as the linear models we have discussed previously, or the decision trees, or maybe we will later discuss neural networks, and other data models. Almost all of those data families have infinitely many members. Therefore, the strategy of summing over all the individual risks simply cannot work, because you will reach the conclusion that the probability is smaller than infinity, which is of course true, but meaningless. So in the following, we will discuss a strategy how to deal with this difficulty. The inspiration or the clever part is that we introduce a delegate event, something that is the logic derivation of the bad event we want to discuss. But this logic derivation derived event is computable, is finite. So the strategy roughly goes, the argument goes this way. As we have discussed, if the event that for some hypothesis in the hypothesis family, this supreme sample means we examine every single hypothesis in the family and check the maximum value of this quantity, and examine if the maximum value of this quantity is exceeding the threshold, which is the same to say there exists at least one hypothesis in the family which makes this quantity exceeding the threshold. They are logically the same thing. So this is the bad event of question, and we consider a logical consequence of this bad event. We will discuss this consequence later. So roughly say is instead of examining the out of sample error of the hypothesis, we employ another training set and consider the evaluated in sample error on the two independently drawn training sets, and compare the discrepancy of half of the tolerance, half of epsilon we'll consider the relationship later, but now the basic inspiration goes this way. If we have the bad event we are concerned with happening, there must be some consequences, and we will examine these consequences. And therefore, because we have said if A derives B, then the probability of B, all the random outcomes that makes A happen must make B happen. Then the range, the area of B must include A, and therefore the probability of B must exceed or at least equal to A. We use this kind of derivation. But this is roughly the logic. The actual derivation is a bit more complicated. We will look into some intermediate event. Something we will see that if A, then we will have some probability that some event C happens, and we will have C derives B. Then we'll see that if by chance that some atom outcome of the random experiment falls within A and also within the portion of A that C happens, then there must be B. And the upper bound guarantee of the probability of A is now compromised by some portion. So let us intuitively show the relationship of A, B, C here. Say what we have said is for the event of A, previously if A derives B, we'll see okay, the area of A must be contained within the area of B, and PA is upper bounded by PB. And now we'll see that if A happens, then with some probability C happens as well. So this is a probability. If A happens, then conditioned on A, C happens. And because C derives B, we will have PB is then includes, or PB is including the area of PC, DC. So, but now, if we want to use the probability of B to bound the probability of A, we need to take into account this portion. Okay, PB, PCA. For an intuitive understanding, we'd like this portion, we are in business if we can establish this portion is large. Because if we do not have any guarantee of this portion, then the probability of B cannot be a very useful upper bound of the probability of A. You would say, okay, I can see the area of B is larger than a portion of A. If the portion is only 0.00001, although I can have B of this size, but I could have, because it's only of a tiny little bit, it only includes a tiny little bit of A, so the actual A could be very large and it cannot be bounded. On the other hand, for now, for example, we can see that this is at least half of A. Then we would see A the probability of A would be at most twice of the probability of B. So that is our plan. Okay, and comes to the two events we are discussing. See, this is Eout. And let us consider this axis as the randomly drawn training data. So see, if we have large probability that the training data, when we join them, it with some probability false, let the E in evaluated this training set is in the vicinity of E out, and with less probability falls very far from the E out. So this is probability density. And if where we are concerning is that E in, we are ignoring the particular hypothesis here. What we are considering is this superb for some hypothesis within H. Okay. Now, if A in is out of the minus and plus epsilon region here, if for some D, the A in D is within these two parts, so that is the event of A. And the event of B we are considering, sorry, the event of C we are considering is that there is another training set D prime where the E in D prime falls within the area of half of epsilon. Then the logic consequence of C will be C and given A will be that the difference between the E in of D and A in of D prime must be at least half of the epsilon. So here is a cleaner representation. Okay. So I haven't write C here. C is represented by this green area. And we can see that the probability of C is, although now the guarantee is only half, but the point is, for whatever kind of guarantee, as long as the threshold has been preset, we can find some large training data set, and so that the Hofstad's inequality guarantees that this green area will take at least some predetermined sized probability. We are not greedy, as we have discussed in this example. We only want the event C happens with 50% of all the cases. Then we will say, okay, the probability of A will be bounded by twice of the probability of B. Okay, this is what we have now. For some sufficiently large n, now we know how sufficient it must be. This will be a trivial question. We'll have the probability of the largest hypothesis within whatever kind of family, which makes the difference between E in and E out greater than epsilon, this probability must be bounded by the probability that there exists some h in the same family that the evaluated AN error on two independently drawn hypotheses exceeding half of the threshold we above mentioned. There are some detailed derivation we will discuss in an actual video. So for now, we established that from now on, we need only to consider this event. Note that we have implicitly changed the data space we are discussing, the sample space we are discussing the random events. This space is of 2n sample space. This space is n data sample space. But the discussion is not broken. They are linked by the logical derivation of the events defined in these two spaces respectively by some inequality relationship.